All right, Joseph, you're the first person here.
Hey, how you doing?
I'm doing all right. How are you?
I'm doing okay.
You must be excited about the test this Sunday.
Uh, um, no, I'm not with the was it quiz 8? Um,
Quiz 8? Yeah.
I I've noticed that the yeah quiz 8 is definitely the one that I wrote down all your notes, and when I tried doing it, I can't figure out how to do. Um, I don't struggle so much with the when it comes down to finding the average rate of change. Those are pretty easy. But when
Okay.
it comes down to the cylindrical containers, um, whenever you have those pictures, the calculated D/R over D, the angle, is the airplane with
Mm-hmm.
1,000 feet. Um, it's just I've been trying. I don't know. I look at the notes and then I look at what you have and then I look. I mean, it's it's that quiz is not clicking with me.
All right.
Or
Well, what, you want to
I
just
think
jump in and try
yeah.
something then? You want to just jump right in and try something?
Yeah. If you don't mind,
Yeah, sure. Okay, so,
yeah.
um,
Do you mind if we start out with?
yeah, go
Go ahead.
ahead. Go.
No, it's fine.
Yeah, well,
What
so
you
you
say?
mentioned the problem with the airplane. So I mean, we can do one like that. The cylinder, we can do one like that. How about you let me know
Yeah,
which one you're most comfortable starting with?
yeah, that's fine. We can
Okay,
start off.
so
You already have that the triangle going, so
okay, yeah, so let's say like this. So uh could you do like delta x over delta theta if theta is 20 degrees and delta theta is, let's just say 1 degree, keep it easy. So is that the kind of problem that you are a little bit intimidated about?
yeah, yeah.
Okay. All right. So this means the change in x over the change in theta. And so you know what we mean by change, right? The problem is like,
Yeah, yeah.
we can't figure this out unless there's some formula that links x and theta together. There's got to be some kind of an equation where if I know theta is 20 degrees, then I can figure out what x is supposed to be, right? Like it would make sense that you would need that,
Yeah.
is what I'm trying to say. Okay, so let's look at this and say, well, I need an equation. That's just the way it is. Unless I'm going to get a protractor and a ruler out and start measuring this stuff, I can't tell you what delta x over delta theta is. Okay, so we need an equation. All right, so can you think of an equation that relates what we have here? Theta's an unknown, it's a variable. X is also an unknown,
I
and
mean,
4 is a
opposite
constant.
over.
Say again?
I mean, wouldn't it be the opposite over adjacent?
Yeah, I mean that is the
That's
relevant equation. So let's start there, right? Okay. Now, my issue with this is that, well, yes, that is a true equation for our situation. And it would make sense to use an equation that's true, obviously, and this one is true. It has x in it and it has theta in it, but that if I'm going to find delta x over delta theta, I need to have it solved for x. Okay, like I need this to say x equals something. It'd be simpler that way. It'd be easier to use it. So are you okay if I say, okay, well, if I solve it, x is 4 times tangent theta? And then that's the way that I need to see it, all right? So does that seem like a reasonable step that I could take?
Yeah,
Okay, so here goes.
yeah,
Here's
that
this.
does.
The change in x divided by the change in theta, if theta is 20 degrees and it changes by 1 degree, is going to be calculated this way. Okay? Whoops. 21 degrees minus 20 degrees over, well, what's x? X is 4 tangent theta, so 4 tangent 21 degrees minus 4 tangent 20 degrees. Okay? So that's it. I know it's a little sloppy because that's this pen I have to use when I do this is just that way. But yeah, this number minus this one, that's the change in x. That's how much this side changes by when this angle changes from 20 to 21 degrees. So just looking at that, does that sound like reasonable enough that that's the change in x over the change in theta with the conditions given as they are?
Yeah,
Okay. And then from here
yeah,
we would
that
just
makes
do this
sense.
on our calculator. And so I'll get my calculator out. I'll tell you what I get. So it's 4 times tangent at 21 degrees, and then minus 4 times tangent 20 degrees. And that turns out to be 0.79. 0.079. Okay, so there's your
Yeah, that's what I got
number.
too.
All right, but that number has some meaning, and it means this, that if I had this triangle and that was 4 feet, all right, and say this angle was 20 degrees, if I bumped that angle up to 21 degrees, that side right here would have to grow by 0.79 feet, okay? But there's your number. So that's the whole process. That we have a shape and we need some kind of an equation, and from the equation we can calculate the changes. All right. As a bonus, if this angle got 1 degree bigger, this side would have to get 0.79 feet taller. All right. So now that we've been through that, if that's one of the things that concerned you a little bit, what do you think about that looking back on it?
Yeah, that makes it simpler. Makes it, yeah, straight to the point.
So,
So I
so
appreciate
is it
that.
just that, like, if we go through it, like when I'm doing it, it doesn't seem that bad. You're just a little bit worried about when you have to do it, when you have to make all the decisions, right?
I mean, I guess it's more just through watching like all the notes or through writing all the notes and then going back through the notes and then trying to figure out what section in my notes applies to this. It's whenever I've just been getting, I guess I've just been overwhelmed with all the
Well, I
material
mean, it's,
from this
you know,
specific quiz.
I can't lie. It's going to take time. Um, and the more you go through your notes, you'll start to realize, okay, there are these problems with the triangles and tangents involved in them. And then there was the problem with the cylinder. And you'll get used to it, but like a lot of things that are complicated, it's overwhelming until you get used to it. But this is just one of many examples that we could talk about that were involved in quiz 7. Okay. Now, so you were
Yeah.
the first one here, so that's why we were talking. We've had a few other people join. I think Kyendra was second to join and Adam was third. So just to fill y'all in, Joseph was the first person here, and he wanted to talk about something from quiz 7, so that's what you're seeing here on the whiteboard. If Kyendra, if you had something that you wanted to ask, then we'll let it be your turn, and then Adam next, and we'll just go through and take turns. If you just want to watch and see what other people were doing, then that's okay. But Kyendra, we'll let it be your turn now if you want to ask a question.
Okay, yes, I was having a little bit of trouble on quiz 7 for 10 and 11. I was just trying to get like a better, like, I guess, understanding of the concepts of like what I was doing on there. Like, I got the answers
Okay.
right and everything, but I was trying to figure out exactly what I was doing.
All right, so I'm gonna look. I'm logged in right now. I'm looking at your quiz 7, and you said questions 10 and 11. Okay.
I have to go back on them because I didn't save them. I was on a work
Yeah.
computer when I did them.
It's fine. And let me just tell you, I'm gonna share my screen, and I'm gonna show you what that looks like. And I don't think it'll be too hard for them to explain those to you. But let's see, share screen. All right. So can you see WebAssign? Can you see, in fact, question 10 on WebAssign?
Yes, I'm going to it now.
Well, you should be able to see it in Blackboard on our Q&A session.
Oh, yeah, sorry.
Okay, so you don't have to log in at all. So all I'm saying is, like, there's a person at point A and they're walking to the right, and then there's this balloon at point B and it's rising. If I tell you this person at point A is walking towards the right at 1 foot, or so what was there, 3 feet per second, could you agree that this side of this triangle is getting smaller? Let's just start there.
Yes.
Yeah, because it says point C is fixed, and point A is where the person is, and they're going this way, they're going to the right. So X, X is the variable here. See how it says what's dx dt? X is getting smaller from moment to moment. So how is it getting smaller from moment to moment? Well, if the person is walking 3 feet per second, then that means the bottom side there, X of this triangle, is getting shorter 3 feet per second. So dx dt is -3. It's 3 because it's changing by 3 feet per second. It's negative because it's getting smaller. So each part of that number plays or tells us something different. The negative says that that's getting smaller from moment to moment, and the number tells us how much. So it sounded like when you brought this up that you felt like you knew the answer, but you were a little bit unsure about the reasons. Is that correct?
Yes.
So as far as the reasons go, are you a little bit more satisfied?
Yeah, it makes a lot more sense, yes.
Okay. And I think there was another one like that. Yeah, this one. So, but basically, if as far as constant rates of change, now notice on both these questions it says the balloon rises at a constant rate and the person walks at a constant rate. Well, anytime we hear that description, that's what the derivative is. The difference about whether something is negative or positive from there is if that variable that's associated is getting bigger or smaller. So that's what I would call the short answer to your question there about question 10 and 11. So how's that sound?
Yeah, that makes complete sense.
Okay, so like I was saying, Kyendra, we'll just take turns between the three of you that are here right now. So now we're to Adam. So Adam, can you hear me? Do you have any questions?
I can, and I do.
All right.
Yeah, I was on the same quiz 7. I just couldn't figure out how to turn the words in Newton's law of cooling into a formula or an equation.
Okay.
So on.
Yeah.
Yeah, it's hard to make sense of.
Well, yeah, it does deal with the fact that it's said that cooling is proportional in a certain way. So let me find that one. I know that was on there, but I don't remember which one it was. So let me look for just a
Number
second.
3 on mine.
It was number 3.
Okay, so gotcha. It says Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the ambient temperature of the surrounding medium. So it's kind of like this. If something is really, really, really hot, it's going to cool fast. Okay.
Mhm.
So like if you take like a pan that was in the oven and it's 450 degrees and you put it in a sink of water, it can like drastically warp its shape because the temperature of the pan is so much different than the temperature of the water. Newton's law of cooling says that it's going to cool very fast.
It was like a reverse hockey stick.
Yeah, so but that's like just what that statement says about the rate of change of temperature. So let's do this. I'll share the screen and we'll highlight each part of that and we'll talk about because your question was about the wording, right? So
Yeah, just like being able to understand it in a way that I could turn it into.
I gotcha. Yeah, so let's see. Rate of change. Okay. So can you see WebAssign okay
Yes.
right now? So rate of change of temperature. So that means how fast it's either warming or cooling. Okay. So the rate of change of the temperature of an object, and let's forget about this word is proportional for now. The difference between the object's temperature T and the ambient temperature T subscript A. So that says how fast something warms or cools is proportional to how different the temperature is of that object from the surrounding medium. Okay, and I'd use the example of a very, very hot pan thrown in a sink of room temperature water. Something very much different happens there if you put a very, very hot pan in a sink of water that's the same temperature or similar temperature. Okay, now when we read the word difference there, well, that's subtraction, okay? So, just strictly speaking from that verbiage, that's T, the temperature of the object as it is, minus T sub A, which is the ambient temperature, the temperature of the surrounding medium, okay? And K is called a constant of proportionality, okay? That just means that, there's some number that fixes this equation perfectly, and it's not known at the moment, but it's there. Anytime something is proportional to something else, there's a constant of proportionality, and whether or not we know what that is, we include it in the statement. Since we don't know what it is, we'll just call it K this time, okay? So anyway, so that was my, believe it or not, quick description of what different elements of this description tell you. Does that make it better or hopefully not worse?
No, yeah, I mean that's in line kind of what I was thinking from reading it. I guess now that I'm finding my notes from when I tried this, what really threw me off was one, figuring out that I needed to map K to I mean obviously there's a constant because it says there, but that it mapped to yeah, I guess that was the one problem I had was like knowing where that kind of fell in. And then the other part that threw me off was the left side of the equation where it's d big T over d little t.
Yeah, so to me that's what might be most important about this, because if anybody ever uses calculus for anything, we got to get, one thing we have to do is learn to read that symbol. So this says the rate of change of temperature with respect to time. And so I'm thinking that means like degrees Fahrenheit per second or something like that. And just think, like, without getting too much math involved, think about like this. Back to the hot pan and the sink of water. Is the temperature of the pan going to change the fastest when it's way different than the temperature of the water, or more similar? Which of those two scenarios is going to cause the temperature of the pan to change the fastest? Well, the more different it is than the temperature of the water. And so, but you could just read this or any other derivative with units of measurement. So this is in like degrees Fahrenheit per minute or degrees Fahrenheit per second. We weren't given enough units to information to actually know what the units were, but it's temperature over time. Okay.
Yeah, that's what
I
missed. That little t was time. But
so, but anyway, the bigger T minus TA is, the faster that dt, capital T over dt lowercase t is going to be.
Okay.
So we put the hot pan in a sink of water. Right at first, it might change at, I don't know, 50 degrees per second. But as the temperatures equalize, then it might change by fractions of a degree per second.
Okay.
So how's that? Is that a decent exploration of that question?
Absolutely. Thanks.
Okay. All right. So well, let's cycle back around here. So let's see, Adam, and then we start off with Joseph. So let's get back to Joseph. Still there, Joseph?
Yeah. Can we look at? Yeah, I'm still here. The number 7. Can you give me an example with that one as well? The consider cylindrical container.
Yeah, sure. Okay, so you could probably understand this without me sketching a picture, but I'll go ahead and sketch the picture. So here's a cylindrical container, and there's water in it, or liquid, or something like that, and it has a certain depth. I'll call it H. So like this container has a liquid in it, we can put a ruler in it, and we could say, well, it's, so many centimeters deep or something like that, okay? Every cylindrical container also has a radius. And so, I don't know, let's say that's 10 centimeters. Okay, so cylindrical container, we know what a cylinder is. The diameter across the top is 20 centimeters, the radius is 10 centimeters, and if there's liquid in it, it has a certain depth, and we'll call the depth H, okay? So far, so good on that. Just for me to appeal to your imagination that this is what our question is going to be about. Now, say I ask you something about how does the volume of liquid in there pertain to how deep it is? I mean, you would think that those two measurements have some sort of correspondence, right? That if I said, I've got this container and the liquid in it is so many centimeters deep, tell me how much liquid's in there. Like, tell me that there's a half of a gallon or something like that. So the volume of that liquid is 100% related to how deep it is, right? So since that's true, and since that's probably the direction we're going to need that equation. So the volume of a cylinder is pi r squared h. It's pi times the radius of the cylinder squared, then times the height or the depth or whatever you want to call it. Now that's for the whole cylinder or any cylinder. For me, if I say that we pour liquid into it, then a liquid takes the shape of its container, so the liquid itself is a cylinder. So I could say that this is the volume of the liquid inside the cylinder, or it's the volume of the cylinder, whatever you want, okay? All right, now, so that's the rough setup for that question 7 on quiz 7. And suppose that I ask you, well, what is dV over dH? Okay, because ultimately that's what question 7 is asking. So that's the derivative of the volume with respect to the depth. Okay, and you can calculate that by just using the rules from quizzes 5 or 6. So when you tell me what this is, when you tell me this derivative or any derivative, you already know the rules, or you've at least been exposed to them if you did the quizzes that came before this one, all right? But if I'm going to calculate this, if I'm going to calculate this derivative or any other derivative, I need that variable on top, which is V volume, to be a function of that variable on the bottom, which is H, or what I'm calling the depth in this case. So unless you have some equation that puts volume V to be a function of depth H, then you don't have much of a chance to find that derivative, okay? Now, this here kind of looks like it might be that. Look at that equation. It looks like if you could plug H in, that you could figure out ultimately what the volume was. So it seems like it seems like it's the thing we need. But what about that R, and what about the pi? Like, what do you do with those? Well, R is the radius, and it happens to be known. It's 10. Pi, that's a constant. If you want to know, pi is a little more than 3, okay? So I can update this and say, all right, V is, so the radius is 10. There it says radius squared, so that's 100. So I'm going to say 100 pi h. All right. Okay. Now, say if I don't mind doing the whole problem for you, like start to finish, but I'm curious to ask you, and if you don't know the answer to this, that's perfectly fine. I'm just curious. With what I have so far, can you tell me what dV over dH is? Do I have enough information on here? And do you know what to do with it?
Didn't you just divide it, the 100 pi over the H? Or
Well, here, I'll give you a hint. It's kind of like this. Suppose y is 4x. What's y prime?
4?
4. This question about the cylinder is just like this one. Believe it or not. Maybe it doesn't look like it, but it is. Here's why. So you see this thing, y is equal to 4 times x. 4 is a constant, right? And x is the variable. See this over here? V is 100 pi times
What is it,
h.
100?
It's 100 pi. 100 pi is that constant. V is the one variable, volume. H is another variable, depth. 100 pi is just a constant. So part of learning to do some math is learning to realize when things that appear complicated because of this notation and the variables and the constants are really as simple as stuff you already know. So anyway, using our rules for the derivative of this function here, V is 100 pi times H, is just 100 pi. Okay? Which on WebAssign it says to round your answer, so that'd be about 314. Okay? All right, Joseph. So there's more that I can say about this, and there's more that I probably will say about it, but how does that sound? If you wanted to just see something that was kind of like question 7 on that quiz, how does that look?
No, that helps a lot. Thank you for that.
Okay, now I
That goes
think
a
it
long
is
way.
important also for everybody to know, what's that number mean, though? Like 314 what? Does that tell you anything? And if you don't like being put on the spot, just tell me, it won't hurt my feelings. But you or anybody else, like, what's the 314 say about this?
Would that be milliliters?
Well, so let's think of our measurements. So in this question, I said, well, it so happens that the radius of the cylinder is in centimeters. Okay. So here's what this number means. It means, okay, I've got units of depth, which is centimeters on the bottom. I've got units of volume, which is, in this case, cubic centimeters. On top, it means that if you had liquid in this cylinder, for every centimeter deeper the liquid got, like if you were pouring it in there, it would gain an extra roughly 314 cubic centimeters of volume. So that's really what calculus is about. And if you use calculus for something as an engineering student or whatever, that's it. Like, it measures changes between variables. For every extra centimeter of depth in the cylinder, we'll get an extra 314 cubic centimeters of volume. Okay. So, all right, so we got the number, but there, as a very important bonus, I gave you the interpretation of the number. Okay. All right, Joseph, since I've got this all up here, is there anything else that you're concerned about or anything else that you need to see about this question?
No, I think that's enough. Thank you.
Okay, all right, so now we're back to Kaindra. So it's your turn now.
Yes, I was actually gonna do that same one, so that explained a lot to me. I think I got it right, but I'm like, because the way that I did it was, I did exactly everything that you did, except for, because they gave it to us in diameter, so aren't we supposed to like cut that in half and then do to the R to the 2 for the radius?
Yeah, exactly. So I'm looking, let me see. So I'm looking at your quiz right now. So it says the diameter is 3 inches. Okay. So that means this is going to be pi times 1.5 squared times h. So I can tell then that it looks like you did all that correct, but mistaking perhaps the diameter for the radius. But you'll get it. You'll get it with that correction.
Okay, then that's it.
All right. So let's go back to Adam. It's your turn, Adam.
Yeah, I had a question on a similar one, but it was having to do with time again. It's time always goes now. It is number 13. I can't find my notes where I worked through this one, unfortunately. I just know it was one that was a problem for me. Yeah, I was thrown off by the fact that T was part of the radius. And T,
Yeah.
Yeah. I guess I was confused how like this volume was growing. Both.
So, well, you could think of it. I mean, first thing is that question on WebAssign is, like a lot of questions in math books, is contrived a little bit, right? But it's derived from a situation where, like, if you had a metallic cylinder and you heated it, it would expand. Okay.
Okay.
So it would expand how? Well, would it expand based on time? Yeah, so it probably, like for every second that go by, the radius could get a little bit bigger and the height could get a little bit bigger. So if you're just wondering to know, like, why would time be involved in the radius or the height of a cylinder? That's the model that we're thinking about.
Okay. Yeah, that's helpful. Because I was trying to figure out, like, if it's pouring, if we're pouring fluid into the cylinder, the
Radius
the
and get
radius of the
bigger.
cylinder doesn't.
Yeah.
But
So
okay,
just
so
think of
that's
like a
fine.
metallic cylinder that's heated. All
Okay,
right.
that'll be helpful. I'll look back at my work and work through it again. I don't think we can go through it.
So you didn't quite get started on that one because
No, I have it somewhere. I just can't find my notes for it. I'm really disorganized right now.
that's okay. Well, you can ask me about it tomorrow if you want to.
Okay.
But at least now you know it's not completely loony to
Yeah.
have time.
Sometimes that
in
throws
there.
me off, so that'll be helpful.
Well, yeah, okay. Okay, so let's see. We're back to Joseph now.
Yeah. I guess if we can look at number 14 and 15. I got a little bit stuck on those as well, just by.
Okay,
So 14 is supposed to see as a constant calculated.
Yeah, I gotcha.
Sorry, go ahead.
Let's see, 14 and 15. So let's do something like this. And I might tell you a little more than you ultimately need to know. One, for everybody else to see, and two, just so I can get a good idea of where it's going wrong for you. But it's kind of like this. Say I had y is equal to 4x squared. Probably would not be difficult for you to tell me that y prime is 8x, right? There's probably no controversy there. Another way that I can do this is, like, somebody might say that I don't need to write down the function and the derivative separately. I can include my work all in one statement like this. I can say, what is the derivative with respect to x of 4x squared? Okay, so that's the way I would read this. The derivative with respect to x of 4x squared. What does it mean with respect to x? Well, that means that x is the independent variable over there. And sure enough, you see the x. Okay, so all right, then that's 8x. Or yeah, 8x. So one way to approach me telling you about that question is I can write these two different things down, or I can write this one thing down and they all convey the same information, that the derivative of 4x squared is 8x, okay? Now that might not be what your concern was. Your concern might be more like this. If I ask you, what's the derivative with respect to x of 4 times kx to the third power minus k squared, where I go out of my way to tell you k is a constant, but I'm not going to tell you what it is, or I don't know what it is. So like 4 is obviously a constant, right? 3 is a constant. But now I'm telling you that even though k is a letter of the alphabet that we spell with, that k is a constant, all right? So, okay, now, would it be with something like this that you're having trouble working through the details of? Like, if I show you how to approach this, okay. So let's see, 4 is a constant, k is a constant. What do the rules of derivatives say when you have a constant times some function of x? What do they say that you're supposed to do with the constant? Those rules say that you carry that constant along. Well, so that's, okay, so we'll talk about that in a second. Okay, it's not 0 though. All right, it's this. This is what we do. So in other words, think of it like this. I don't want to get in too many places at once, but look at this problem and look at this problem. Is it true that this problem and this one have all the same numbers, right? And 2's a constant, isn't it? And 2's a constant, right? But we treat constant different ways when they're in different places. And all that comes down to the rules. Like, well, there's unfortunately, there's no nice and fun way to do it. You just have to learn what the rules are. In this case, this top one right here, that constant there, 2, yes, it's a constant, but what we're supposed to do with it in that case is leave it where it is and multiply it times the derivative of x to the third power, which is going to be 6x. All right, this constant, on the other hand, x to the third power plus 2, well, that's a term, too, that's just a constant all by itself, right? It's in a totally different spot. The rules apply to it differently. So the derivative of x to the third power plus 2 is going to be 3x squared. Sorry, I forgot my squared there, but so you see how, like, these two problems involve all the same numbers and all the same constants, but they are different. The rules that apply to them are different. So back to down here. So if I say, what's the derivative of the constant 4 times k times x to the third power? Well, we'll carry that constant over into our work and multiply it times the derivative of x to the third power, which is 3x squared. Okay? And then what did the rules say that we do with the minus? Well, you carry the minus. And then what's next? The derivative of k squared. Okay, what's the derivative of k squared? Well, if k is a constant, then k squared is also a constant. And the derivative of a constant all by itself, like that, is 0. Okay? So that's how I would look at it, going into fairly good detail on what you do with each component of that. But you'll have to tell me. I mean, all this comes down to is if you understand what I'm trying to get you to see. So Joseph, how's that look, at least getting this far? Okay. So if you can agree that, if you're going to agree that I applied the rule correctly and all that, then let's see, what can I do? I got 4 times k times 3 times x. I might as well multiply 4 times 3. So let's say 12, 4 times 3, k is a constant, I don't know what it is, times x squared. That would be your final answer. All right, 12kx squared. Now, just as a warning, or like a word of caution to everybody in the class, is that if I were to write down the rules for derivatives, notice the difference between this one and this one. Okay, so this first function says that y is some constant k times some function f of x. The rule there says y prime is k, that constant, times f prime, the derivative of this function, whatever that might be. This case, when it says y equals some function f of x plus a constant k or minus a constant k, then our rule says the derivative is f prime of x being whatever the derivative is of that plus 0, okay? And so essentially, like, that plus k right there does not factor into the answer. So I guess, like, this one, to me, brings up a lot of things that we probably should talk about. But Joseph, you'll just let me know, with all that being said, how's this one look? Ultimately, this one in the middle here, this was the one I wanted to show you. This is the one that's like what you mentioned on the quiz. You think you're okay with that now?
Yeah, yeah, that makes sense.
So just be careful with the rules because just from having taught lots of calculus classes before in the past, it can be tempting to say that the derivative of a constant is 0, but that can be misleading. All right, that's not really always true. What would always be true is the derivative of a constant all by itself is 0. Okay. All right, so let's go back to Kaindra. So it's your turn.
Okay, I think that was all for me. So I was just kind of watching everything else to make sure I was doing everything right and stuff.
Okay, so I'll just, in that case, I'll go back between Adam and Joseph, and if you change your mind, you can raise your hand or you can turn your mic on and just let me know. How's that sound?
Yeah, that's perfect. Thank you.
Okay, anytime. So then we're back to Adam. Looks like Adam lost connection, so let's see if I can answer anything for you, Joseph. I don't know how long it's going to take Adam to reconnect, but we'll make do.
Yeah. Let's see what else. I guess one I haven't answered yet would be number 6, but I think I can still figure that out. But
Let me see, question 6.
it's the one with the satellite and the Earth.
Yeah, and it does help you through part A a little bit. If you let me see, is Adam back? Joseph, no. I think he's having trouble. Well, you let me know. We can try to do one that's a little bit simpler that involves an angle in it somehow. I'll have to leave it up to you. Whatever you think would help you the most to see.
I mean, yeah, something simpler would be fine, just to give you an idea.
So let's see, 5, yeah. So you're right, 5 does involve the angle and the derivative. 5 would be a good one to do. But let's see, so it looks like Adam's back. So how about, since I was
Yeah, you can
gonna
go back to
have
him. That's fine. Yeah,
his turn,
yeah.
then we'll do that one next for you.
Sorry.
So Adam, did
Yeah, that's
you
fine.
get a good connection?
Yeah. Yeah, I had a question about 14 on the second quiz of this section. What number is it? Quiz 8.
So that'd be
Uh,
quiz 8.
Yeah.
Quiz 8, let's see. Okay, so quiz 8, and then I don't know if I heard.
Number 14.
Okay, quiz 8, 14.
Yeah, I don't know if I missed a video session or something on this one. But my intuition on that is that the the denominator there's like a apostrophe. So I'm wondering if that just means that's like the local derivative of that term.
Oh, okay. Yeah, so I have to. You have a very good eye for detail, Adam. Let me show you what I mean. So, okay, so here we are looking at question 14. Can you see question 14?
Mm-hmm.
So you're talking about that apostrophe,
Yeah.
which turns out is actually a comma.
Ah, okay.
So it says, I know that seems weird because we use that apostrophe for derivative, right? Prime.
Yeah.
So this is WebAssign's fault. I take no responsibility for their type, but it's like it's saying your function is y is 25 at the point 0, comma 1. All right. If it was me, I would have used the word at, because nobody's going to think the word at means derivative or anything like that. So, so what you would do is, I'm sorry, what?
Do you use LaTeX to put the problems in?
WaTeX?
Yeah.
Yeah, that's what they use. Like in some of these questions, you can tell the ones I've written, like this one, because I'm not very good at WaTeX, and so I just import pictures for the ones that I do. But yes, that's what they do.
All right. Yeah, that was my question.
So
I just want to make sure I didn't like misunderstand something about that.
No. That was, and like I don't have a good eye for that kind of detail. I wouldn't have even noticed that. So that's why I said you had such a good eye for detail. So with that being said, do you think your 14 doesn't pose too much of a challenge?
Yeah, no, that's too fun.
Okay, yeah, you definitely didn't miss any videos on that or anything. So let's see. Here we are. Okay, whiteboard again. So is that everything then for at least this turn, Adam?
Yeah, thank you.
Okay, so Joseph, we were going to do the problem about the angle and the derivative, I think. I guess I have short 5. Okay, I was gonna say I've got short-term memory problems sometimes. 5, yeah, 5. Okay, so that'd be. Do you want to do? How about this? Let's just do question 5 from the quiz, with the same numbers and everything. All right. And in case you don't have, or anybody doesn't have WebAssign up, I'll just recreate the picture. Okay, so there's like me right here, and then there's this plane, this airplane, and it's flying this way, and me and my line of sight to this airplane and its level flight path make a right triangle. All right, and so it's given that there's this angle theta right here. Okay, and that angle theta, that could say, well, this is how far from directly above me my line of sight is to the plane. Okay, so I might say I see the plane from a 40-degree vantage point, where that's the angle that I'm talking about. Anyway, okay, and then we say that this plane has a level flight path of. All right, Adam, take care. Good luck on that test. So the plane has a level flight path of 1,000 feet, okay? And then we'll say that the distance that the plane is horizontally from me is r. So like from here to this point directly above me, we're going to call that r, all right? So that's the description of the problem. That's how I would describe what we're seeing and what everything is. And then the question is actually saying, what's dr over d theta when theta is 40? Okay, so here we go. Question, dr over d theta under the condition that theta is 40 degrees. Okay, all right. Now, so see if you can remember. And again, I don't at all want to put you on the spot, Joseph, and not everybody likes that, but I am curious if you know. Earlier, what did I say that we needed to find for this derivative? Like if I want to find what dr over d theta is, what do I need to start with?
The angle?
Well, I need a function. Okay. So every single
sorry, you need
time.
to get, since we're given
So I need. I need
I mean, we're giving
R.
R, and then so that'd be the opposite over the adjacent.
Well, yeah, that's true. So yeah, you're getting there. I mean, I think you'd probably figure it out, but I wanted to say something kind of in generic terms, such as I need R, this variable, to be a function of theta, that one. Okay? That's for all derivatives, every problem. This variable on top needs to be a function of that one on the bottom. All right? So let's do what you're saying. We'll work an equation in and we'll get it into that function. So is it true that tangent of an angle in a right triangle is the opposite side, which in this case is R, over the adjacent side, which in this case happens to be 1,000 feet? Okay, so that would be a true, right? That's a good place to begin, isn't it?
Yeah.
Okay, but is this enough? Do we take the derivative of this?
We have to apply the angle somehow.
Well, so we need R to be a function of theta. What's it mean if R is a function of theta? It means there's some formula where I plug theta in and I get R back out. So would you be comfortable if I rearrange this way?
Yeah. You're right.
Okay.
Sorry.
Now, but tell me, like, and this is not just for you. I'm not saying that I don't think you know this, but just in case people watch the recording or anything, is this equation such that if I plug theta in and I do the math, it will tell me what R is?
Yeah, it would.
Yeah, I mean, that's exactly how this is arranged. And that's what I mean when I say R is a function of theta. I mean that if you plug in theta, if you know what theta is, it will tell you what R is supposed to be. Okay? So I say all that just to say that to find the derivative dr over d theta, I need R to be a function of theta. I need to look at this picture and think of all the math I've learned and get some equation where if I plug in theta, the angle, it will calculate R, this opposite side, all right? Okay, now once you get that, the derivative, dr over d theta, is just the derivative of that formula, 1,000 tangent theta. So what's the derivative of 1,000 tangent theta? It turns out that's 1,000, because that's a constant, times the derivative of tangent theta. What's the derivative of tangent theta? Secant squared theta. Okay? So just to summarize, here's the sequence of steps. To find the derivative dr over d theta, get R to be a function of theta. Once you get there, use the rules that you know to find the derivative of that function. In this case, the function's 1,000 times tangent. The derivative of that is 1,000 times secant squared. Okay? All right. So next we put 40 degrees in. It says calculate the derivative dr over d theta when theta is 40. So I'll do that this way. Everybody can do this part with their calculator in however way they want. This is the way I would do it, though. Okay, so I'll get my calculator and I'll tell you what that is. So I take cosine of 40 degrees, I square that, and then I divide 1,000 by that number, and then I get 1704.08. So 1704.08, and that number is a lengthy decimal and it has to be rounded. Okay. All right. Now I haven't done all the question yet. I've got most of it, and so let me pause here for a second and ask you what your reaction to it is so far.
Oh yeah, that
So,
definitely makes sense. It's I need to focus more, I guess, on as well on the derivatives of like changing up the secant with tangent and I guess
yeah.
cosine and sine. I guess the name parallel. I had a list of them, but they're somewhere in my notes. I need to pull back out.
Well,
Or,
I gotcha. Well, so again, I think when we started this session, um, it's when if I'm doing the problems, it seems like you understand all my steps. You're just not quite to the point where you're ready to be totally on your own yet. Would that be fair to say that?
yeah, yeah,
Yes.
yeah. I think I just struggle with watching videos. I'm more of a whenever I'm working a problem out, I like to have I guess like the answer for that problem, and then I can plug in the numbers until I get the answer, if that makes sense. I'm really used to doing that. That's kind of the best way that I've like for myself to I guess learn. And with this with this type of like with WebAssign, it doesn't give me the option to where I can't do that and have to just watch your notes and then go back and try to solve it without knowing the answer. So I don't have a like a point of reference, if that makes sense.
Well, so you can there is a textbook that goes along with WebAssign that has problems in it. Like, so if you're saying like, well, I want to say do problem 15, but I want to look in the back of the book to see what the answer to problem 15 is, and then kind of work between them. Is that right?
Yeah, yeah. I think I have
So
to do that.
you can access the textbook through WebAssign if that's what you want to do in addition to just doing the quizzes.
Yeah, I think I'm gonna have
Okay.
to do that.
Yeah. So I mean, if that's something that you need, but also I need to say one more thing before I finish this one. The units here are in units of r, which is the side of this triangle. Well, that would be feet over the units in theta, and for derivatives and trig functions, the units for an angle are always going to be radians. So this is in feet per radian. And the question on the quiz said to give the answer in feet per degree. Okay, and so I just, as a disclaimer, I have not totally finished this one. Taking it here would get you all the way, but I'm thinking I may have showed you what you wanted to see, Joseph. But how about this? Based on what I have there, is there anything else that you want to ask about the individual steps or the big picture or anything else you can think of?
No, I actually I'm looking at the because I already had an answer plugged in on there, and it was the same number that 1704.08.
Yeah,
Or I guess
okay.
I hadn't transferred over to feet.
Yeah, so it's got to be feet per degree. But you convert that because 1 radian is 180 over pi degrees. So if you just divide by 180 over pi, that'll convert it to feet per degree. But all that says is that, so the answer that you'll end up getting is about 29.9.
Divided by. Sorry, did you say for feet to that conversion? What was that again? So 180.
So yeah, so here, let me write it down. 1 radian is 180 over pi degrees. So that means a radian is about a 57-degree angle. Okay, but there's your conversion. So if you take this number 1704.08 and you divide it by 180 over pi, yeah, so that will convert it, and you'll get about 29.9 feet per degree. So that means that if this angle changes by a degree, then that plane will get about 29 feet closer. So if you're looking at it and there's this angle that determines which direction you look to see it, so 1 degree change in that angle means that plane moves 29 feet through the air, right? Because obviously the angle changes to track the plane's movement if you're looking right at it. But anyway, that would be an interpretation of what the number means. All right.
Okay, yeah,
Anything
that
else?
makes, yeah.
Because, well, that's what we're really
No, I
learning with
think
calculus
that's-
now. Oh, go. I'm sorry, I interrupted you. I didn't mean to do that.
Oh no, I was agreeing with you.
Okay. Well, so I'm going to need to get to my next session here pretty soon, but let me make sure that everybody's okay. So, Kyandra, if you have anything else to ask, let me request that you do that now.
No, everything was perfect. Thank you so much for your time.
Hey, anytime, and glad you could join, Joseph and Kyandra. And if you need help between these sessions, just reach out to me and I can make time for you. I'm going to make the test available tomorrow, and you can work it from, anytime until it's due at that point. How does that sound, everybody?
Thank you.
All right. Well, if you
Hey.
need any help tomorrow, let me know and I can help you out. Take care.